Welcome back, students. Let's start doing the exercise problems in lesson 2. Let me start with 2.1. Two charges 5 into 10 power minus 8 coulomb and minus 3 into 10 power minus 8 coulomb are located 16 centimeters apart. At what point on the line joining the two charges is the electric potential 0? Take the potential at infinity to be 0. Okay, so 2.1. So there are two charges, 5 into 10 power minus 8 coulomb and minus 3 into 10 power minus 8 coulomb. So there is this one and there is another charge, and they are separated by a distance of 16 centimeters. 16 into 10 power minus 2 meters. First one is 5 into 10 power minus 8 coulomb, that's the charge here, and here it is minus 3 into 10 power minus 8 coulomb. So they want you to find the point along this, the line joining the two charges. Okay, along this line, they want you to find out where the potential would become 0. Okay, one thing is sure. Let's do it this way. Okay? Let us suppose that the potential is 0 at some point here. Okay, and let us suppose that I am going to take this as the origin. O. Okay, this is the O. And what is this distance is going to be? This distance, I'll say this to be, I'll say like maybe from here I can take this to be x. This is going to be 16 plus x centimeters. Okay. So at this point, the potential due to this and the potential due to this must be the same in magnitude, but then the sign will be opposite, because like you have negative charge here, so you have a negative potential here, and then you have positive charge here, and then you must have a negative positive potential here. So when you combine these two, then it can become 0. So potential at this point P, let's see, potential at point P, we'll call it as Vp, is equal to potential at P due to the positive charge here plus potential at P due to the negative charge here. Okay. Then what is the potential due to the P, the plus charge at P? Vp plus is equal, this is 5, and here this would be K Q by R, so that is simply 9 into 10 power, I'll just keep it like that, because I'll say KQ1 by R. Okay. And we'll put the numbers later. KQ positive. R. Now what is Vp minus? Vp minus is equal to saying KQ minus by R. Okay. So they should be equal, but then the signs are opposite, then automatically they will cancel, right? So I'll say okay, this is R plus, and then I'll say this is R minus. R plus is this distance, R minus is this distance. Okay? So I'll do this then. So this must be equal, because Vp is negative and Vp plus is positive. So Vp plus plus negative of Vp minus, that should be equal to 0. Okay. So this is a condition, correct? So what I'm going to get here, I'm going to get K Q plus by R plus is equal to K Q minus R minus. K and this will cancel, so R minus into Q plus must be equal to Q minus into R plus, right? So what is this? R minus is how much? Just x, right? So Q plus is 5 into 10 power minus 8 coulomb into Q plus is 5 into minus and R minus is this x. Yeah, x is equal Q minus is 3 to 10 power minus 8 into R plus, it's actually 16 plus 6. So I can cancel 10 power minus 8 here, so it becomes simple. So I get 5x is equal to 48 plus 3x. So when you bring it here, 2x must be equal to 48 and x must be equal to 24 centimeters. Okay, x must be equal to 24 centimeters. So from here, from the positive charge, it will be 24 plus 16, 40 centimeters away, and from the negative charge, it is simply 24 centimeters. So you can do it like this. Or if you want to keep the numbers and prove it properly, this is enough. I can do it, right? So Vp plus is equal how much? So 9 into 10 power 9 into Q plus is 5 into 10 power minus 8 by 16 plus x. And what is B? P minus, same 9 into 10 power 9 to what is this one? Minus 3 10 power minus 8 by x. So this is going to be a negative number, right? It's a negative number here. Right? So then what is Vp? So Vp can be written as 9 into 10 power 9 into 5 into 10 power minus 8 by 16 plus x plus this number is going to be minus 9 into 10 power 9 into 3 into 10 power minus 8 by x. Okay. So when I sum these two things, it must be equal to 0. So that should give me 9 into 10 power 9 into 5 into 10 power minus 8 by 16 plus x minus 9 into 10 power 9 to 3 into 10 power minus 8 by x is equal to 0. So this will result in 9 into 10 power 9 into 5 into 10 power minus 8 by 16 plus x is equal to 9 into 10 power 9 into 3 into 10 power minus 8 by x. Okay. You come back to this expression. So 9 will cancel, 10 power 9 will cancel, 10 power minus 8 will cancel. So you are reduced to 5 by 16 plus x is equal to 3 by x. So when you do it, it's going to be 5x equal to 48 plus 3x. Same equation we got here. So here I use the numbers. When I did it here, I didn't use the numbers. I just took the magnitude alone. So notice here, even though it provides a negative potential here, it goes to the other side, then you don't have to consider the sign of the charge. Here you consider the sign of the charge. And that resulted in a negative number here. So it went there to the other side. So we got only positive. So that's understandable. So one is positive, other one is negative. So you say 5 minus 5 is equal to 0, or you can say 5 is equal to 5. So that minus 5, you can ignore the sign. So typically that's what we've done here. But even if you had done it clearly in the numbers, you would have got the same equation, and that will result in x being equal to 24. Okay. So this is how you do the first problem. And then the second problem, 2.2. So regular hexagon of side 10 centimeter has a charge 5 microcoulomb at each of its vertices. Calculate the potential at the center of the hexagon. So that's easy again. Okay. So 2.2. So you have a regular hexagon. So you have 5 microcoulomb at the vertices, 5 microcoulomb, 5 microcoulomb, 5 microcoulomb, 5 microcoulomb, 5 microcoulomb. And I want you to find the potential at this point, at the very center. Okay. If you were to find the electric field, you can readily say that it's going to be 0, right? Because you have the same charges, plus 5, plus 5, plus 5, plus 5 here. So if I keep a unit positive charge, then this is going to repel with certain amount of force, and this will also repel the same amount of force, so they will get cancelled. Okay, so this would be, there won't be any force here. So the same thing will happen here, same thing will happen here too. So the electric field would have been 0. But would be the same thing for potential? No. So the potential at this point is actually the potential due to this, potential due to this, and potential due to this, and potential due to this, potential due to this, and potential due to this. Okay? Since they are all of the same type, all the potentials will add up, right? Suppose if I had minus 5 here, the potential would have cancelled. Because for 5, you will have some value, a positive value, and for minus 5, you would have had a negative value, that would have cancelled. Okay? But in this case, all the charges are positive charges, so you will have a potential at the center, a net potential at the center, but you won't have a net field at the center. So, as I was describing to you when we were talking about all this, you can have a potential without a field. Okay? And you can also have a field without potential. We saw that. When we discussed conductors, we came across that because we said the potential, inside the conductor there is no field in the static condition. But then you have done some work till you reach the surface of the conductor, because there will be a field outside it, and within the conductor you are not doing any work. So whatever work you did up till the surface of the conductor would remain the same. It wouldn't get changed. So potential inside the conductor will have some value, but E will be 0, is what we discussed when we discussed conductors. This is something similar, though it's not a conductor. The key idea is you can have a potential without a field, or you can have a field without a potential. So that's the idea. Anyway, so we'll get here. Okay, this is 0. I'll say it's O, origin. So voltage origin is, okay, I call it as A, B, C, D, E, and then F. These are the vertices of this hexagon. So VO is actually equal to potential due to A plus potential due to B plus potential due to C plus potential due to D plus potential due to E plus potential due to F. Okay. And what is the potential due to this? Well, this is a point charge. So at a distance r from here, I should have a kq by r will be the potential, right? Okay. kq by r will be the potential. So this would be kq by r will be the potential. This is also positive charge, and this will also be the same distance from there. So you will have kq by r as a potential plus kq by r as a potential, all of them. Since it's not a vector quantity, you don't have to worry about this being cancelled. Okay, one thing being cancelled by another thing. You don't have to worry about that because it's a scalar quantity. And you all have the same type of charges, positive charges, so there won't be any negative effect. Okay, you won't be able to subtract from anything from here. So you will only have addition. So kq by r and kq by r, it is 4, and kq by r and plus kq by r. So you're going to get 6 kq by r. That will be the potential at the very center. 6 times that. Okay, so now what is r? They said if the distance between these two charges is 10 centimeters. Well, if this is 10 centimeters, what is this? Okay, you can do it in two ways. The simplest way is this. So if you take a hexagon and if you do something like this, then this is 60 degrees, right? Do 60 degrees, 60 degrees. In case of a regular hexagon. So it's an equilateral triangle. So if this is 10 centimeters, this should also be 10 centimeters. Suppose if it were not an equilateral triangle, then you need to find this angle and then you need to find this length from that angle. Okay? Because you know this side, so maybe you can draw something here. Okay? So this will get divided into half, so you will have 5, then you have this here, hypotenuse, then hypotenuse into cos 60 is equal to 5 centimeter. So what is hypotenuse? Hypotenuse would be 5 centimeter by cos 60. Cos 60 is 0.5. So 5 by 0.5 would be 5 into 2. So that should give you 10 again. So you can do it another way also. But the simplest explanation for all that is this, that since you have an equilateral triangle here, all sides will be equal and they have given you the value of one side, which is 10 centimeters. So this must also be 10 centimeters. So that is also clear, right? So once we know what the value of r is, then I can substitute all the values in this equation to find the potential at that point O. Okay. So that would be 6 into 9 into 10 power 9 for k. The q is 5 into 10 power minus 6 because microcoulomb. So divided by this r is 10 centimeters. So 10 into 10 power minus 2. Okay. So meters. So 10 power minus 2, I have 10 power minus 4, and then I have 5, I have 2 here, and I have 3 here, then 3 into 9. So voltage at the very center is going to be equal to 27 into 10 power 9, 10 power minus 4, 10 power 5 volts. This is how you do this problem. Hope it's clear to you. Okay, 2.3 is a simple problem and there is nothing for me to work out. So two charges, 2 microcoulomb and minus 2 microcoulomb are placed at points A and B 6 centimeter apart. Then identify an equipotential surface of the system. And B is what is the direction of the electric field at every point on this surface. So identify an equipotential surface because you will have infinite number of equipotential surfaces. So you just want you to identify one such surface. And if you go through your textbook, when they talk about the equipotential surface, they also give you the shape of the equipotential surfaces you would get when you have positive and negative charges. So one of the surfaces could be mentioned for this problem or drawn for this problem, and the direction of the electric field at every point on the surface will be perpendicular to the surface. At every point on the surface, the field will be perpendicular to the surface. So it's a very simple problem, so I don't have to do it on board. So I'll go to example 2.4 now. A spherical conductor of radius 12 cm has a charge of 1.6 into 10 power minus 7 coulomb distributed uniformly on its surface. Then what is the electric field inside the sphere and just outside the sphere and at a point 18 cm from the center of the sphere? Okay. So 2.4. A spherical conductor, so you have a spherical conductor. of radius 12 centimeter. So they are given you radius 12 centimeter, radius, as a charge of 1.6 in the 10 power minus 7 coulomb. So the charge is equal to 1.6 into 10 power minus 7 coulomb distributed throughout the surface uniformly. Then what is electric field inside the sphere? The field inside the sphere, you know, it's going to be 0. The field inside is going to be 0 clearly. And just outside the sphere is on the surface of the sphere. For that, we know the charge which is on the sphere behaves as if it were concentrated at the center. We talked about it right before. So just on the surface, just outside the surface, the field is going to be E here is simply going to be K Q by R squared. So this is R, so E here on the surface is going to be K Q by R squared, because all the charge here would behave as if they were concentrated at the center. Okay, we did that before. Or the other way of doing it is, we saw using Gauss law what the field on the surface of any conductor would be, right? So it was, if you remember, we derived E was going to be equal to sigma by epsilon naught. That was the derivation we had. So that is surface charge density divided by epsilon naught. Well, again, it will be the same as this one. So that, why? Because what is sigma? Sigma is going to be this Q, in this case it's going to be Q by, what is the area? 4 pi r squared. That is your sigma into epsilon naught. Okay. So what is this anyway? So 1 by 4 pi epsilon naught is actually K. So this results in KQ by R squared only. It's the same equation. Either you can do it from this perspective of considering all the charges to have been concentrated at the center and then start doing it here, or you can just use this formula. The electric field on the surface of a conductor is given by sigma by epsilon naught. Sigma is the surface charge density. So even if you do the surface charge density, think here it will be equal to this. So we can do it very easily. So what is E here on the surface? So on the surface, E on the surface is equal to KQ by R square. KQ by R square. So 9 into 10 power 9 into 1.6 into 10 power minus 7 coulomb, and divided by 12 centimeter, right? So R square, 12 into 10 power minus 2 into 12 into 10 power minus 2. So this will go, I get minus 3 here. So 1.6, right? I can slightly change it. So 10 power 9 I have. Okay. So 9 I'm going to write as 3 into 3 into 10 power 9. So for 1.6, I'm going to multiply that by 10 and divide that by 10. Or I can take one of the 10s here and then use it here. So I can have 10 power 8 into 16, 10 power minus 3. Okay, that should be fine. And that is equal to 12 into 12. Okay, this 16 can be written again as 4 into 4. So notice here, this 4 into 3 cancels with 12, and this 4 and this 3 cancels with 12. So 10 power 8 into 10 power minus 3, and that is actually equal to 10 power 5 Newton per meter. So that is the electric field intensity on the surface of this conductor. Do it very easily. And what's the third part? The third part is at a point 18 centimeters from the center of the sphere. That's clear, right? So the third part is at a point 18 centimeters from the center. So you're talking about some point here, which is 18 centimeters from the center. That's 18 centimeters. So let's say if we were to do this E18, E at 18 centimeters is equal to same kq by r square. For this point, the charge will behave as if it was concentrated at the center of the sphere. So I'm going to use this kq by r square expression again. So that's going to be 9 into 10 power 9 into 1.6 into 10 power minus 7 divided by r now is 18 into 10 power minus 2 to 18 into 10 power minus 2. Okay, so this will become 1, 2 now. This will be 36 here, 36. So 10 power minus 2, 10 power minus 2, minus 3. So I can probably do this. This 6. So 1.6. 1.6 and 10 power 6. Top, so I'll say 16 into 10 power 5 divided by 2 into 18. Okay, so I can have a 16, 4, okay, so 4 fours are 16, and here it's going to be 9 fours, right? 16 by 36, 4 by 9. So 4 by 9 into 10 power 5 Newton per meter would be the field at this point. So that's how you do this problem. This is more lesson number 1 problem than lesson number 2 problem. Okay. Next, 2.5. A parallel plate capacitor with air between the plates has a capacitance of 8 picofarad. What will be the capacitance if the distance between the plates is reduced by half and the space between them is filled with a substance of dielectric constant 6? Okay. So let's see, 2.5 now. 2.5. You already have a capacitor, a parallel plate capacitor, and its value is 8 picofarad. 8 picofarad is equal to 8 into 10 power minus 12 farads. Okay. So what do we know now? For a parallel plate capacitor, C is actually epsilon naught A by D. Okay. So this is equal to this value. So what are they doing now? Now they are reducing the distance of separation between the plates by half. So what is the new capacitance for this? So capacitance C dash is equal to, if you reduce this distance, then you will have epsilon naught A by D by 2. Right? Instead of D, the distance is reduced. Instead of this distance, you reduce the distance now. From here, you went from there to this one, which is D by 2. Okay, that gives you 2 will go up, so you will have 2 into epsilon naught A by D. But you know this. This for epsilon naught A by D, you have 8 into 10 power minus 12 farads. Okay, as a value. And now you have not stopped with that. Once you reduce this, you also included a dielectric material, a substance into it. You inserted that into this material, to this capacitor. So then what would that do? If I insert from here, if I insert a dielectric material like this, between the plates, and they said that this is the constant, dielectric constant K is equal to 6. K is equal to 6 now. Right? Yeah. K is equal to 6. So what will happen to this capacitance? We know this. Once you have this thing, then C double dash is equal to K into epsilon naught A by okay, it's going to be K into C dash now, which is also equal to K times 2 into epsilon naught A by D. Okay, so what is K? K is 6. 6 into 2 into epsilon naught A by D, which is the original capacitance, right? What is that? That is 8 into 10 to the power minus 12 farads. So I got 12 into 8 picofarads. So that would give me 96 picofarads. So what have we done here? We have taken a capacitor with certain A and then a certain distance of separation, and air was inside, which is pretty much I can treat that to be equivalent to vacuum. Okay, so the capacitance of this arrangement was given as 8 picofarad, but I also know the C is equal to epsilon naught A by D. So epsilon naught A by D is equal to 8 picofarads. Okay. Now what have I done? I have reduced the distance of separation between them. So when I reduce the distance of separation, then I would have a different capacitance now. So instead of D, I have D by 2. So then I increase the capacitance. My capacitance becomes double. And I don't stop with it. I insert a dielectric substance of a dielectric constant 6. So then that will become C double dash is equal to the K into this C, right? And then which is C dashed. So this is what I get, and I get 12 into the original C, this C. This is original C, right? Okay, so that is going to give me 96 picofarad as the answer, and that is how you do this problem. Okay, let's do problem 2.6 now. 3 capacitors, each of capacitance 9 picofarad, are connected in series. Then what's the total capacitance of the combination? Then what is the potential difference across each capacitor if the combination is connected to a 120 volt supply? Here it is 2.6. It should be easy. So you have you're connecting. I'll use another pen. This is the battery, the voltage here, and then I'm going to connect it to 3 capacitances in series. Okay, the difference between a battery and a capacitor is that both the lines are of equal size, but here the negative is smaller than the positive one. Okay, so that's the difference anyway. This is 9 picofarad. This is also 9 picofarad. 9 picofarad. Okay, I'll call this as C1, as C2, and call this as C3. Then what's the effective capacitance of this circuit? That's easy. We saw it. If you connect capacitors in series, then the effective capacitance will be C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. So that is equal to 1 by 9 picofarad plus 1 by 9 picofarad plus 1 by 9 picofarad. That gives you 3 by 9 picofarad. So then C is equal to the reciprocal of that, and you get 3 picofarads. It's pretty straightforward. Okay, so that is the answer to that question, A. Then the second part of it is this voltage is 120. Then what would be the voltage across each capacitance? Then that's clear, right? So you have this here. The potential difference between these 2 points is 120. So what would be the potential difference between these 2 points and these 2 points and these 2 points? Okay. Suppose this is going to be positive, this is going to be negative, positive, negative, positive, negative. Okay. And this will also be positive and this will be negative. You see, all the charges will be equal, right? Because we connected them in series. All the charges will be equal for all the capacitors. And in this case, the capacitance is also the same. So, what is the voltage across a capacitor? The voltage across a capacitor is given by this expression, right? The basic expression is this. C is equal to Q by V. So, we want V, we want to get Q by C. Okay. So, then C1 will be Q, okay, V1 will be Q by C1. And V2 will be Q, this is V1, this is V2, this is V3. Okay. So V2 will be Q by C2, V3 will be Q by C3. In this case, the C's are also the same. C1 is equal to C2 is equal to C3. So, because you connected the capacitors in series, the charge on each capacitor is going to be the same anyway, and then the capacitances are also the same. So, the voltage across them must also be the same. Okay? So, V1 must be equal to V2 must be equal to V3. And what else do we know? We also know that V1 plus V2 plus V3 must be equal to V in this closed circuit. Okay? So, we know that V is equal to V1 plus V2 plus V3. And what is V1? V1 is Q by C1, V2 is Q by C2, V3 is Q by C3. But then, what do we know? Since C1 is equal to C2 is equal to C3, then this expression becomes V becomes Q by C plus Q by C plus Q by C. So that gives you 3 to Q by C. Or that Q by C can be written as one of the things, right? It's going to be 3 into, I can write this as a V1 or V2 or V3. Okay? So then my V1 is going to be equal to V by 3. So this is 120. That 120 will be equally divided. Okay? That's going to be 120 by 3, 40 volts. Okay? Because you have the same capacitances and because you have the same charges, the potential across each capacitance would be the same value. And the sum of the voltages will be equal to the applied voltage. So because V1 is equal to V2 is equal to V3, so now you have 3 times V1. And the 3 times V1 must equal to this 120. So V1 must equal to 40 volts. Okay? So this is how we do this problem. It is 2.6. And how do you do 2.7? In 2.7, 3 capacitors of capacitances, 2 picofarad, 3 picofarad and 4 picofarad are connected in parallel. Then what is the total capacitance of the combination? And then determine the charge on each capacitor if the combination is connected to a 100 volt supply. So that's also easy. Right? 2.7. If I connect capacitors in parallel, okay, C1, C2, C3, then we saw that the effective capacitance C was equal to C1 plus C2 plus C3. Okay. So what is C1? C1 is 2 picofarad, and then C2 is 3 picofarad, and C3 is 4 picofarad. So that is equal to 7 plus 2, 9 picofarad. That's effective capacitance. So I can replace all these things with just one 9 picofarad capacitance, and the charge on the 9 picofarad capacitance will be equal to the sum of the charges here. Okay. So the charge is supplied by the battery. Okay. Okay. So this is it. And the second part is this: like they want you to find the charge on each of them. When you connect them to 100 volts supply. Okay, so I'm going to connect it to 100 volts supply now. Okay, what is the charge on C1? The 100 volts is going to be applied equally. So this is going to be okay. The voltage across C1 is 100 volts, and the voltage across C2 is also 100 volts, and the voltage across C3 is also 100 volts because they are connected to the same points on the battery. Okay. So C1 we know, right? What is C1? C1 is equal to Q1 by V. So what do you need? I need only Q1, right? So Q1 is equal to C1 to V. So likewise, Q2 will be equal to C2 into V, and Q3 will be equal to C3 to V. As simple as that. So that gives me, what is Q1? C1 is 2 picofarad, 2 into 10 power minus 12 farad, into what is V across C1, that is 100. That is going to be equal to 2 into 10 power minus 10 coulomb. And what is Q2? Q2 is this is Q1, this is Q2, this is Q3. So Q2 is actually C2 into that voltage across it, 100 volts. So that is 3 picofarad, 3 into 10 power minus 12 into 100. So that's going to give you 3 into 10 power minus 10 coulomb charge. And C3 again 4 into 10 power minus 12 into 100. That gives you 4 into 10 power minus 10 coulomb. So now you have found the charge on each capacitor. So the total charge that the battery has to supply is equal to Q1 plus Q2 plus Q3. So if you add it all up, so Q into Q1 plus Q2 plus Q3, that would be equal to 2, the 10 power minus 10, 3 10 power minus 10, 4 10 power minus 10. So that is equal to 9 into 10 power minus 10 coulomb. Okay, or 0.9 nanocoulomb charge. Okay, so that is the total charge. Q1 plus Q2 plus Q3. Okay, because you see there are 3 paths and the battery will supply charges to the 3 paths. Here there is only one path, so the battery can supply the charges only to the first plate. Here there are 3 paths, Q1, then Q2 and then Q3. So each capacitor could have different charges. So combine them all, so I get that. So this is how we do this problem. It's 2.7. Hope it's clear to you. Okay, let's do problem 2.8. In a parallel plate capacitor with air between the plates, each plate has an area of 6 into 10 power minus 3 meters squared, and the distance between the plates is 3 millimeter. Then calculate the capacitance of the capacitor. If this capacitor is connected to a 100 volt supply, what is the charge on each plate of the capacitor? Okay. So it's a simple problem. So 2.8. A parallel plate, there are 2 parallel plates here. So it's a parallel plate capacitor, and then they say the area of this plate is actually equal to A is equal to 6 into 10 power minus 3 meters squared. 6 into 10 power minus 3 meters squared. And the distance is 3 millimeter. Okay, the distance between this is equal to D is equal to 3 into 10 power minus 3 meters. So 3 millimeter. That's what I said. So now actually it's air between the two plates. If air is like vacuum only, so epsilon naught can be used straight away. So what's the capacitance here? Capacitance for parallel plate capacitor is given by this expression, epsilon naught A by D. Epsilon naught is 8.854 into 10 power minus 12, and then A is 6 into 10 power minus 3, and then D is 3 into 10 power minus 3. Yes, one is meter square and that one is meter. So this is the capacitance. So this capacitance is equal to, okay, if I do that, if I take this 3, and it's roughly 9, right? 8.854 is roughly 9. So I'll say approximately equal to. So roughly 3. Right? And then this 10 power minus 3 and 10 power minus 3 will go. So 3 into 6 is 18. 18 into 10 power minus 12. So 18 into 10 power minus 12 farads. So that is equal to 18 picofarad. Roughly equal, slightly less than that, because it's not exactly 9, it's 8.854, but roughly it is equal to 18 picofarad. That is it. And what are you doing here? You are going to connect it to a 100 volt supply, and what is the charge on each plate of the capacitor? Now you take this and then you are going to connect it to a 100 volt supply. 100 volt supply. So what is the charge? So you are going to have positive charge here and then negative charge here on this plate. So now you need to figure out what is the charge on that. So that's easy again. So we know that C is equal to Q by V, which gives you Q is equal to CV. C is given here as 18 picofarad and V is 100 volts. So Q is equal to 18 into 10 power minus 12 into V is 100. So it will be 18 into 10 power minus 10 coulomb, or 1.8 nanocoulomb. So you can say that is equal to 1.8 nanocoulomb charge. So this would be a positive 1.8 nanocoulomb charge, 1.8 nanocoulomb charge, and this would be negative 1.8 nanocoulomb charge. So this is the charge we are going to have on the capacitor. Okay. So it's a very simple problem. It's 2.8. So let's look at problem 2.9. So 2.9, you see, explain what would happen if the capacitor given in exercise 2.8, a 3 mm thick mica sheet of dielectric constant 6 were inserted between the plates. So what will happen when you insert a 3 mm thick mica sheet? Okay, so that is what we are going to do now. So the same capacitor, same area and same distance, but then between these two plates, and we are going to insert a dielectric material now. Okay, same thing. Everything else is same. Okay, this is 3 millimeters. So usually the same A as given, 6 into 10 power minus 3 meters squared. I have inserted a dielectric material, and the constant is 6. Here K is equal to 6. Dielectric constant is 6. Now the first question is this: while the voltage supply remains connected. So what will happen when you insert it? When the voltage supply is connected, it remains connected. Let's put it this way. 100 volts. So what will happen? Initially you have this charge. What is the charge? You had 1.8 nanocoulomb, right? So you had 1.8 nanocoulomb charge was there. And then for this capacitance, the voltage across it was 100 volts. So we calculated that. So 1.8 nanocoulomb charge would be here on the capacitor. Now I am going to insert this material. That's what I say, right? We are inserting it while this remains connected. I hope you understand the problem. You have this capacitor. 2.9 talks about 2.8. So you have this capacitor. The battery is connected to it. Now you are inserting this 3 millimeter dielectric material into it. Then what will happen now? Well, clearly, because you are going to insert this dielectric material, the capacitance of this capacitor is going to increase. Because you know what is the new capacitance? The new capacitance is equal to K times old capacitance, right? K times old capacitance, because K epsilon naught A by D. So the capacitance is going to increase 6 times now. This K is 6, so the new capacitance is going to be equal to 6 times 6 into 18 picofarad. So this is what is going to happen. So you get 108 picofarad capacitance. Right now we would have 108 picofarad capacitance. Because of inserted here. So now, so what will happen here? This 100 volt is going to remain the same because it's going to get connected there. So now you increase the capacitance. So what will happen to the charge? Because you know this condition has to be met, right? What is the condition? Q is equal to C into V. The condition has to be met here. In this case, C dash to V. V is not going to change. We will remain 100. But C dash has changed here. So what will happen to Q now? So C dash is 108 into 10 power minus 12 of pico and then 100. I'm going to have 10 power minus 10. So 108 into 10 power minus 10 coulomb. Or you can say 1.08 into 10 power minus 8 coulomb. That's manipulation is up to you. You notice that from 18 10 power minus 10, it has become 108. So you can clearly see that the charge itself has increased 6 times. Thus you kept connected to the battery. Now we are inserting it. As we are inserting it, then what happens here is that the capacitance has increased, and because the capacitance has increased, more charge will have to be flowing from the battery to make the voltage equal to the applied voltage. The other way of understanding it is this. Because of the presence of the dielectric material, the field inside would be reduced, right? Whatever field you had here, that would be reduced. We knew that. Okay, so suppose if this was E, and now the moment we insert this material, then what will happen is that the original E naught would become E naught by K. That's a new E. Now this E into this distance will not be equal to 100 volts because you reduced it by 6 times. So you need to put more charge to produce a field which will eventually give me the voltage across this being equal to this. That's the other way of looking at it. You can either think that the capacitance has increased, so for the same voltage you will now have more charges. That's one way of looking at it. The other way of looking at it is, because I am inserting a material here, the field inside would be reduced for this particular charge. Whatever charge was there before would be reduced. So, but that field into that distance must be equal to this voltage. So, which means that the E must be increased. Will be increased only if you have more charges on the capacitor. So more charges will flow from the battery to the capacitor. So that is how the capacitor is increasing its capacity. So you can take it either way. Okay, that's it. So that's the first part. Now the second is, after the supply was disconnected, I mean you are inserting it all right, but then the supply is disconnected. So what will happen in that case? Well, first, what does it mean? I have this capacitor and then I connected 100 volts across this. Then it put me some charge Q. What is the charge? It is 1.8 nanocoulomb. Plus, I want to see it. 1.8 nanocoulomb charge. Now I removed the battery. I have disconnected the battery. So now the charge is sitting on this capacitor. The charge is now sitting on the capacitor. When this charge is sitting on the capacitor, I am inserting this one. Notice the difference. In the first case, you have not removed the battery. In the second case, you have removed the battery, but now you are inserting the dielectric material. So what would the dielectric material do? Clearly, it will reduce the field inside. How much would it reduce? How much would the new field be? Well, the old field was E naught here. Now we have inserted the dielectric field, so the new field is going to be E naught by K. So we reduce like that. Okay. And what is the potential now? What is the potential now? Because the net field is zero. The net field is reduced, and the potential across the plate will also be reduced. So V must be equal to ED. Okay. So which is equal to E naught by K to D. So E naught by D was 100 volts. E naught into D, this potential was 100 volts. So it is connected to 100 volt battery. So it was 100 volts before. Now, so E naught by D is equal to V naught. Okay. You had 100 volts before. So you are charged it to 100 volts. Now you are inserting a dielectric material. So the potential difference across that would be V naught by K. So that can be written as 100 by 6 volts. So we will have roughly approximately 16.6, right? 16.7 volts. So you have the capacitor plates. Then you measure the voltage across, you charged the capacitor with 100 volts battery, then you disconnect it. When you are charging, the battery puts some charges on the capacitor. You disconnected the battery. Now you measure the voltage across the capacitor, because the charges are present, will read as 100 volts. Now what you do, you insert a dielectric material between the two plates. Now the voltage will show you a reduced voltage. It will show you about 17 volts. From 100 volts, it will come down to 17. And if you remove the dielectric material, it will go back to 100 volts. You see, you are not changing the charge here. Whatever charge you had remains the same. You are putting the dielectric in and then removing the dielectric. If you put the dielectric in, then the voltage across the two plates will become 17. You remove the dielectric and it will go back to 100. Okay? And the charge will not change. But in the first case, in this case, you kept the battery connected to it. So, then also, because of the presence of this dielectric material, the voltage will reduce. But since the voltage reduces, and you have battery connected to it, then the battery will put more charges. The charge will start flowing from the battery to the capacitor, because the capacitor has low voltage and the battery has high voltage. So the charge will keep flowing till this voltage equals that voltage. So in that process, the charge would have increased as it happened here. But here, you first charged and removed the battery. The battery is no longer involved. The charge remains the same. It's not going to change. So you put a dielectric material, voltage across the plates of the capacitor comes down, and you remove the dielectric material. Then the voltage goes back to 100 volts. Hope this is clear to you. Okay, we will do problem 2.10, the 10th problem. A 12 picofarad capacitor is connected to a 50 volt battery. How much electrostatic energy is stored in the capacitor? Very simple problem. So it's 210. You have a 12 picofarad capacitor. This is 12 picofarad capacitor. This is connected to a 50 volt battery. Okay, this 50 volt battery. And how much electrostatic energy is stored in the capacitor? Well, because you are connecting a battery, you keep charging the battery, so the charges will go and accumulate, and in the process of charging, it will have done some work. So the charges are sitting there. So that is what you call as the amount of energy stored. So what is the work done in doing it, or the amount of energy stored? One of the three equations is half C V square, and if you know one equation, we will get the other two by substituting the value for V and C. Okay, using this expression, C is equal to Q by V. Okay, so instead of C, if I put Q by V, then I will get some other equation. Or instead of V, I put Q by C, then I will get another equation, the second equation. So, but then I can remember this, and if I take the values and substitute here, what I'm going to get? Half into, what is C? That is 12 into 10 power minus 12 farad multiplied by 50 into 50. Okay, so this is going to be 6, and then this and this I'll take, and this will become minus 10, right? So 25 into 6. So 25 into 6 will be 150 into 10 power minus 10. So 150 into 10 power minus 10 joules, or I can say 1.5 into 10 power minus 8 joules. So that is the amount of energy stored in this capacitor. It's very simple problems, nothing complicated about it. It's straightforward application of the formula. Take the values and then substitute those values in the formula, then we are going to get the result. Then the last problem, 2.11, the 11th problem. A 600 picofarad capacitor is charged by 200 volt supply. It is then disconnected from the supply and is connected to another uncharged 600 picofarad capacitor. So how much electrostatic energy is lost in the process? So something similar to it we have already done during the lesson when we are doing an example problem. So it's something similar to that. Okay, except that the numbers vary, the idea is the same. So initially you had a 600 picofarad capacitor, and then it is charged by a 200 volt supply. So you charge it to the voltage across this is actually equal to 200 volt supply. So you charge it now. So this may be plus, minus. Okay, so you will have a certain amount of energy in it. So what is energy in this? I will call this as initial energy, Ui. So you will simply have CV square. So this is going to be half into 600 into 10 power minus 12 into V is 200 into 200 V square, right? So it's very simply you can remove this. So there are 2 zeros here, 2 zeros here, 2 zeros here, 6 zeros. So I'll get 10 power minus 12 into 10 power 6. So I'll get 10 power minus 6, and then 6 into 2, 12 into 10 power minus 6 joules. This is the initial amount of energy stored in this capacitor. So what I am doing here, I am going to take this capacitor and connect it to another 600 picofarad capacitor, another 600 picofarad capacitor, and let us see what happens now. So I'll take this capacitor and then I'll connect it to another 600 picofarad capacitor. So what is going to happen is 600 picofarad. So also 600 picofarad. So what will happen? We said that the charges will start flowing from this capacitor to the other capacitor. This is a charged capacitor, this capacitor, and I am connecting one more capacitor here. So this is a higher potential, a lower potential, so the charges will start flowing from here. So there will be charge sharing that will take place. Or you can do it you can look at it the other way. Like you have a conductor here, you have another conductor, you are connecting both of them. So clearly the charges will flow from this conductor to that conductor, and ultimately both of them will be at the same potential. Right? This must be at the same potential, this will be the same potential. So when the potential across this is equal to the potential across this, then the charge sharing will stop. Okay? We derived expressions for that, if you remember. Like we took C1 and C2, two different capacitances, and then we took Q1 and with Q2, then we said Q1 by C1 must be equal to Q2 by C2 because the voltage across this must be equal to the voltage across that in the final condition, and from there we calculated the energy and stuff. Okay. Then there was the expression that we came up with, which was something like so V1 is equal to C1 by C1 plus C2 into the original V. Okay, this is what we got. So in this case, so what is happening is C1 and C2 are the same. So V1 or the voltage across one capacitance will be equal to V by 2. It is the same. So C1 by 2C1. So V by 2 is what we will get. Right? Because capacitances are the same. So the voltage, the final voltage will be half of the original voltage when you connect another capacitor of the same capacitance. If the second capacitor has a different capacitance, then the final voltage will not be half of the original voltage. That will be governed by this formula. Okay? But since C1 is equal to C2, we are going to get V by 2. So 200 volts was before. Now the final voltage will be 100 volts. Okay? Here also is 100 volts. Then what is the energy in this capacitor? Let's say this is, then we will have a reduced. Minus. Okay. So 6. Then we're equally sharing the charges here. This identity. Okay. So that's it. 3. That's all this. Okay. What's the energy in this capacitor? That is going to be half C V squared, which is equal to half into what is C? It is 600 picofarad into 10 power minus 12. And what is V? V is now 100 because so V1 is actually 200 by 2 is equal to 100. 100 volts, so 100 into 100. So if you do that, then this will be 3 and 2, 6 zeros, minus 12. So 10 power minus 6 will get 3 into 10 power minus 6 joules in one capacitor. The other capacitor will also have the same energy, right? So this is energy in capacitor 1, and then energy in capacitor 2 is also equal to 3 into 10 power minus 6 joules. So now what's total energy in the capacitor? So U final is equal to U1 plus U2, that is equal to 3 into 10 power minus 6 joules plus 3 into 10 power minus 6 joules. So that gives you U final is equal to 6 into 10 power minus 6 joules. So the original energy was 12 into 10 power minus 6 joules, so 12 microjoules, but now you have only 6 microjoules in the capacitor. So 6 microjoules is lost. So the loss in energy is equal to UF minus UI, which is 6 into 10 power minus 6 joules minus 12 into 10 power minus 6 joules. So that is equal to minus 6 into 10 power minus 6 joules. So when you say minus, it is you have lost energy, you have not gained energy. So lost energy. So this amount of energy has been lost by way of electromagnetic radiation, heat and electromagnetic radiation. Okay. So this is something that we already come across in one of the example problems in this lesson. It's the same type. The problem is of the same type. There you had different numbers, but the idea was the same. And I generalized it with C1 and C2. But here C1 and C2 are equal. Even in that problem also C1 and C2 were equal, but then we derived an expression for the general case when C1 and C2 are not equal. Okay? Try to go through that derivation, and that's it. So you get this voltage thing, how the voltage, what voltage they will settle. The initial voltage will be half only if you are going to connect the same amount of capacitance to this capacitor. Okay. If the connected capacitance is different, then the voltage would not be half of the initial voltage. For example, it's 100, it came down to 50, but that is only because C1 and C2 are the same. But if C1 and C2 are different, then it could be 60 or 70 or even 45. No. Okay. So the more charges you give to the capacitor, then the less the voltage will be across this capacitor, the donor capacitor, the capacitor that gives charges. So anyway, so that's like go through that derivation, and that governs this basically. Okay? So with that, we have come to the end of the exercise problems, and with that, this lesson also comes to an end, and we will start the next lesson in the next video. We'll start lesson number 3 in the next video. Lesson number 2 is over.